Hello, welcome to topic 2, cryptography. This is going to be the only sort of pure mathematical, well, it's not the entire topic, but you will be doing some number theory to understand how to sign things digitally and make them secure. So here's the lecture notes. And this is what we're going to cover in 4 different videos. This is the first one on hash functions. We're going to understand what a hash function is with some examples. The value returned by a hash function, not surprisingly, is called a hash, although some people call it a digest, computer scientists. In fact, in cryptography for blockchain, we most often call it a hex, because with cryptographic hash functions, these are called cryptographic because they only go one way. If you see the hash or digest, or we're going to call it hex most of the time, hash or hash, they mean the same thing. If you only know the hash, then you don't know what the original message that was encoded by the hash function is. For example, the SHA, Secure Hash Algorithm family, there's lots of them. Ethereum uses SHA-3, actually it's now moving to some more sophisticated encoding as well, called zero-knowledge snarks, some of these terms. All right, we'll get onto those later. But SHA-256 is a pretty old one. It maps any data of any size to a 256-bit number. That's why it's called 256. So here's a hash calculator. If I say, for example, hello world, oops, I can't spell hello. Here's the output. This is a 64-digit hexadecimal number. So we have to explain what that is next. So let me put that down there and carry on. So we know about binary numbers. We did those in the introductory lecture. But people find hex a lot more convenient because very, very, very long strings of ones and zeros, it's much more difficult to remember 256 ones and zeros. You might possibly remember 64 hexadecimal numbers, though, if you just want to memorize, for example, your private wallet key. That's a hexadecimal number with a few dashes to help you remember the strings. So we can convert binary to hex. We can convert decimal to hex. Here's binary to hex. So if I put in some long string of ones and zeros, whoop, then that's what it is in hexadecimal. Okay, so these letters are actually numbers as well. A is actually the number 10 because it's to the base 16. Whereas with the base 2, we only needed zeros and ones to convert to binary. With 16, we need 15 numbers that are just taking up one space. So the numbers in hex go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then A, B, C, D, E, F. A, B, C, D, E, F. That's 6 up. So that goes to 15. And we don't need more than that because we've gone all the way around. And it doesn't matter whether it's capitals or lowercase, it's the same thing. We can also convert Ascii text to hexadecimal. This is not the hash function, but it's going to look the same. It's not going to be the same output. So if I put hello world here, that becomes a hexadecimal value, but it's not 256 bits. There's not, I've put them in pairs here, but it's not 64 of them. Whereas if I put it into the hash function, you always get the same thing. In fact, with a hash function, it doesn't matter how long the message is. make a longer message now and calculate it, it's always going to be the same. Whereas just converting Ascii using the American Standard Code that converts letters to binaries, it's slightly different. Anyway, so anything can be converted to binary, pictures, videos, movies, and to hex, because there's an equivalence between them. Let's just do an example of this. You've got an example on the slide there. I'm just going to put my webcam on, and just to recall, if I want to convert the number 30 to binary, then I want to go to powers of 2, 2 to the power 4, that's 16, 2 to the power 3, that's 8, 2 to the power 2, 2 to the power 1, that's 2, and 2 to the power 0, that's 1. 2 to the power 1, and 2 to the power 0. Okay, and 30 is less than, the next one would be 2 to the power 5, which is 32, so it's too big. So I have to write 30 as 16, that's the biggest one, and then adding 8 to 16, that's fine, that's 24, it's still less. Add 4, that's 2 squared. Adding 4, what is that, 16, 24, 28, that's all right, plus 4, and 2, but not the 1. All right, so that in binary means I've got none of those, but I've got one of those, one of those, one of those, and one of those. So that's 30 in binary. But what about 30 in hex? So for hex, I start with 16 to the power 0, of course, and that's always the 1 that you need if it's an odd number. And then 16 to the power 1 is just 16. And then 16 to the power 2 is 256. So I don't need that, that's too big. So I have to write 30 as 16 plus 15, isn't it? So there are 15 ones, and there's one 16. So in hex, and I'll begin OX, so we know it's a hex. So there's 1 16 and 15 in hexadecimal. Let's just do it again. There was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is A, B, 10, 11, C, D, E, F is 15. So it's 1F, and I can write it lowercase or uppercase, it doesn't matter. So this little OX at the beginning makes it clear. On the slide there, 23 is 17. And you'd think that was a decimal, wouldn't you, unless you had a 0x in front of it. All right. Now, let's talk about the properties of a good hash function. They have to be very quick. When I did it on the internet with a calculator for SHA-256, it was instant, of course. Deterministic, which means that if I put the same message in hello world, exactly the same, and don't change anything, then I will get exactly the same output. And if I change a tiny thing, that's the avalanche effect, then I always get a completely different hash, or it's called a digest here. So here's an example of a 160-bit cryptographic hash function, because there are 40 hexadecimal numbers here. However long the message is, it's always going to be the same length of output. That's determined by the hash function. And you see these slight changes here with typos, you get completely different. That's called the avalanche effect. So we also need these properties called collision resistance and pre-image resistance. And that means it's one way. What does collision resistance mean? Well, here's an illustration of the avalanche effect with SHA-256. So if you put the same inputs, hello, then you'll get the same outputs, okay? If you just change a tiny bit, like take off the exclamation mark, you get a completely different hash. Collision resistance means that if you put two different messages in, you never, well, almost never, very, very, very minuscule, negligible probability that you might get the same hash. And pre-image resistance is if you know the hash, then it's not feasible, absolutely impossible to find the actual message that gave you that hash. And that one-way function that they're impossible to invert is why they are so good at encoding information. So how do they actually work? How do they get that same length output every time? Well, there are two elements. First of all, an initial hash, which can be randomly chosen, some 64 length hexadecimal number, or more generally an n-bit hex. And we'll call that Ascii for the initial hash. And then some compression algorithm. So that's the encoding part. So you put your input, some Ascii or equivalent sort of binary code or whatever it is you want to put it in, and then you translate it, as I showed you with the converters, to a very long hex. Now, that hex is unlikely to be exactly like 7 times 256 if it's a 256, if n is 256. So you might have to pad that hex at the beginning on the left, putting lots of zeros where it doesn't matter. So that you get an exact multiple of n bits for your hex. Then you can apply the compression algorithm, which is probably easier just to go to the next slide, which illustrates it. So suppose you've got a message that's 1,000 bits and n is 256. Now, 256 doesn't go in exactly to 1,000. 4 times 256 is 1024. So we're missing 24 bits. We have to pad the message with 24 zeros to the left, not to the right, because you'll be changing the number then. But you won't change it if you put the zeros to the left. And then you've got exactly 4 blocks. And you take the first block, in this case called block 0, and you take the initial random hex, and then you comply this mixer, this compression function, and that will give you another 64 length hexadecimal number, a 256-bit decimal number, hexadecimal number. And then you take this block, which is 256-bit, and hash it with that to get another 256-bit S2. And you just proceed along in that way, hashing block by block. These aren't blocks in a blockchain, by the way, they're just a block of 256 bits. And then you get the final output, as we've seen on the SHA-256 converter. So how are these hash functions applied? Well, one of them, applications which is commonly used, is an integrity check. So suppose you send Fred a message and you and Fred both know that your hash function is SHA-3, but you're doing it 4 times, because you can always hash again. You can take your hex, make it the input, and hash again. So you can keep hashing, and it's impossible. There's lots and lots of different hash functions. And if somebody just knows the hash and they don't know what the hash function is, they're never going to find the message. So to see if your message was changed, you can attach the message hash with the message. And when Fred gets them both, he applies your known secret hash function to the message and checks that his hash is the same as the hash you sent. And if it's not, then the message was corrupted. And another application, message authentication code, is a picture here. Suppose that Alice and Bob share some secret key. Alice and Bob are the names we give to people in cryptography. Fred also, because it begins with F. So there's Alice, Bob, Carol, Dave, Eve. Eve is always evil. Okay, she's trying to intercept, and Fred, and so forth. Okay, So Alice and Bob share a secret key, and Bob can verify that Alice possesses some information. Alice just says, I know this, but I'm not going to show you the information. You just need to verify that I know this. At the end of this topic, we'll be doing a very similar exercise using these zero knowledge snarks, which sound horrendous, but they're actually not that bad. It's just the name. So it's possible to verify that you have information without actually revealing the information. Now, Bob has the information, so he just, he doesn't know that Alice has got it, but he hashes the information and compares the hash that he gets. So here's the information. There's the MAC, message authentication code, which is the hash, which uses their shared secret key algorithm. And that's transmitted to Bob. He's also got the information. He applies it and he gets his MAC, his hash, and then he compares the two. And if they are the same, Bob verifies, yes, you have that information. If they're not the same, he says, no, Alice, you haven't solved the problem. Try again, or something like that. Okay? So that's used in all the password verification that you put on the internet, detecting corrupting files as well, and for validating transactions in blockchains. I think that's it for this video. So say goodbye, and the next one will be a little bit of number theory.